Hello everyone, I'm Shuhao Cui from Institute of Computing Technology, Chinese Academy of Science, supervised by Shuhui Wang. I will introduce the work named Towards Discriminability and Diversity, Batch Nuclear Norm Maximization, under label insufficient situations. In label insufficient situation, there are not enough labels, resulting much unlabeled samples near the decision boundary, which lacks prediction discriminability. To improve discriminability, a popular method, entropy minimization, tends to classify samples into fewer categories, resulting in less prediction diversity. Thus, we reanalyze the prediction discriminability and diversity by looking at the batch matrix A composed of prediction responses for randomly selected B samples on C categories. Prediction discriminability could be enhanced by minimizing Chanel entropy, since F-norm and entropy have strict opposite monotonity. We could push matrix A to the minimum of entropy by maximizing the F-norm of matrix A. Prediction diversity could be measured by the predicted category number, which means more predicted categories result in more prediction diversity. For two different predicted responses, if they belong to different categories, they are linearly independent. But if two responses belong to the same category, the differences are little, and they could be regarded as approximately linear dependent. Considering that the biggest number of linear independent vectors is called the matrix rank, then the matrix rank could represent the predicted category number, also the prediction diversity. Two conclusions in math. First, the nuclear norm of matrix could bound F-norm. Second, nuclear norm is the convex approximation of the matrix rank. Accordingly, we propose batch nuclear norm maximization, in short BNM, an approach to maximize the nuclear norm of the batch response matrix, which could simultaneously maintain prediction discriminability and diversity. When batch size and category number are 2, matrix A could be represented by two variables of x and y. Then we could calculate the entropy, F-norm, and nuclear norm as follows. Then entropy and F-norm could reach optimal when x and y are either 1 or 0, which makes sure the prediction discriminability. But nuclear norm could reach optimal when x and y are 1, 0, or 0, 1. This means x and y should not be equal when optimal, and the diversity are maintained. We apply our method to 3 label insufficient situations, which is semi-supervised learning, domain adaptation, and unsupervised open domain recognition. In this task, BNM is always cooperated with classification loss on labeled source domain, and loss could be calculated by only one line code in PyTorch and TensorFlow. In supervised learning, there are fewer labeled samples and rich unlabeled samples. There are no explicit domain discrepancy and category differences in semi-supervised learning. Experiments show that BNM could improve ResNet baseline and other existing methods, such as VAT. Thus, BNM is more suitable for cooperation with existing methods for semi-supervised learning. For domain adaptation, there exists large domain discrepancy between labeled and unlabeled samples, but the categories are the same. Experiments show that BNM outperforms many existing methods, and BNM could also cooperate well with existing methods, such as CDAN. Thus, BNM formulates a basic method for domain adaptation. Supervised open domain recognition. There are large domain discrepancy between labeled and unlabeled samples. Some categories do not even exist in labeled samples, denoted as unknown categories. Experiments show that BNM could achieve state-of-the-art results, and we also visualize the ratio of unknown categories. Results show that BNM could maintain the ratio of unknown categories. Thus, BNM could formulate a simple state-of-the-art framework for unsupervised open domain recognition. For more, you can contact me by email and GitHub, and I'm seeking jobs these days. Welcome to contact with me. Thank you for your listening.